Dear students, I welcome you in this lecture on comparison test in absolute form. First, we will study dominance of one series by another series. So, first let us define what is dominance of series. The series AN is said to be dominated by the series Bn if there is positive integer n such that mod an is less equal to mod bn whenever n is greater equal to n. In this case, we write that as a notation an is dominated by bn. You read this as an is dominated by bn. We also say that bn dominates an. Let us see, let me revise this definition. It is very important definition for convergence series of real numbers. So we say that the series AN is dominated by series BN if and only if there exists n belongs to I, that is positive integer n, such that whenever n is greater equal to n, mod an is less equal to mod bn. So in this sense, we say that the series an is dominated by series bn, or that series bn dominates series an. Let us see some examples of dominance. So series n is equal to 1 to infinity an, I will take this as series n is equal to 1 to infinity n is clearly dominated by the series n is equal to 1 to infinity n square. This is first example. Let us see second example. Series n is equal to 1 to infinity 1 upon n cube is dominated by series n is equal to 1 to infinity 1 upon n square. So in some sense we can say that dominating series have terms whose absolute values are greater equal to absolute values of corresponding series which is getting dominated. So I may call the series AN as smaller series. So I may call this as series with smaller absolute value terms, or simply smaller series, and I may call the series Bn as bigger series. Bigger series in the sense that absolute values of its terms are greater equal to absolute values of corresponding terms. Not all terms, except for few finitely many terms, this holds. This means what does this relation means? This relation means that except for few finite terms, all terms of series Bn have absolute value greater equal to corresponding absolute values of series An. Okay. We are now in a position to see comparison test for convergence in absolute form. Two things are given in the statement. An is dominated by Bn, this is first statement, and secondly Bn converges absolutely, then An also converges absolutely. In notation form, we could write this as if An is dominated by Bn and if mod Bn converges, then mod An also converges. So let us see some examples. We have already seen examples of dominance of series. Now let us go through the proof of this result. The proof of this theorem makes use of the basic fact that series of non-negative real numbers is convergent if its sequence of partial sums is bounded. So here the series Sn is taken as a sequence Sn is taken as sequence of partial sums of the series mod An. So we have to prove that this sequence is bounded or convergent. Further, M is taken as value of the series, and note that any partial sum of the series will always be less equal to this value of the series because it is given that mod Bn is convergent. So let us begin by considering a partial sum Sn. We are considering partial sum Sn for n greater equal to n. We are considering this. Consider partial sum mod Sn which equals to mod a1 plus mod a2 plus mod an. Note that mod an will appear here because n is greater equal to n. Then rest of the terms are mod an plus 1 plus mod an plus 2 plus mod an. Now we are going to use this fact that if mod an is less equal to mod bn whenever n is greater equal to n, so this fact is being used here. These terms are used using this fact. So next step is that this whole expression equals to the first part is kept as it is. Now this step is kept as it is. This is a partial sum, we may say, or a part of partial sum, and any partial sum is always less equal to value of series for series of non-negative real numbers. So as such this expression is going to be less equal to this. So again the first part is kept as it is, but this expression is nothing but m, so it is equal to m. Thus we proved that Sn, the sequence Sn of partial sums is bounded by this term, by this whole expression. Sn is bounded, the sequence, let me put in this way, the sequence Sn of sequence of partial sums is bounded by this number. So if sequence of partial sums is bounded, then we know that the series of non-negative real numbers is bounded. Then the series is convergent. Okay. So thus, let me repeat the last step. Sequence Sn of partial sums of non-negative series is bounded. Hence, we can say that the series mod an is convergent, that is series an is absolutely convergent, and hence it is convergent. Before we study divergence In comparison test in absolute form, let us revise the basic result that geometric series x raised to n converges if and only if minus 1 is less than x is less than 1, that is mod x is less than 1. I have provided you detailed proof of this theorem in notes, and some part we have proved in earlier lecture as well. Okay. Let us proceed to see the divergence of series of real numbers by using comparison test in absolute form. So the basic statement or the statement of comparison test in absolute form is An is dominated by Bn if if mod An diverges, then the series mod Bn also diverges. In notation form, we could read this as if series An is dominated by series Bn, if series mod An diverges, then series mod Bn also diverges. So two things are given, dominance and divergence of series mod An. Let me repeat the statement in a simpler way. If series An is dominated by series Bn, and if smaller series in the sense that mod An diverges, then the bigger series is also divergent. So we are going to use the basic ideas here. The sequence Sn is defined as the sequence of partial sums of the series n is equal to 1 to infinity mod An. Then sequence Tn is defined as sequence of partial sums of the series n is equal to 1 to infinity mod Bn. Note that we are going to use the basic result that sequence of or series of non-negative real numbers is convergent if and only if its sequence of partial sums is convergent or bounded for series of non-negative real numbers. So since this is divergent, we can say that this sequence of partial sums is not convergent and hence not Cauchy. Further, if it is not Cauchy, then we are going to prove a relation, and by using that relation Tn will be non-Cauchy. If Tn is non-Cauchy, then series Bn then series Bn will be divergent because Tn is not convergent or not Cauchy. So that will be, this is the idea of the proof. Let me repeat the idea. Mod An is divergent, hence Sn is non-Cauchy. So Tn is also non-Cauchy by using a relation which we are going to prove. As Tn is non-Cauchy, series is Bn is divergent. This is the idea of the proof. So let us begin by considering the mod, the difference or distance Tm minus Tn, where m is greater than n, greater equal to n. This difference is clearly equal to mod Bn plus 1 plus mod Bn plus 2 plus mod Bm, because first n terms gets cancelled. Now using this fact that if n is greater equal to n, then mod An is greater equal to this. So corresponding terms of this sum, this sum are greater equal to corresponding terms of this series. Okay. And this is equal to mod Sm minus Sn. So thus what is proved, that we proved that if n is greater equal to n, if n is greater equal to n, then mod Tm minus Tn is greater than mod Sm minus Sn. Okay, so this is what we proved. Now consider the argument. Again we are going to use the basic result that if series of non-negative real numbers is divergent, then its sequence of partial sums is unbounded. So series an is mod an is divergent, hence its sequence of partial sums is unbounded. By using this relation, we can say if sequence, let me add one step prior to using the relation second. If Sn is unbounded, then it is not Cauchy sequence. If it is not Cauchy sequence, then by using this we could say it is the sequence Tn is not Cauchy, because mod Tm minus Tn is greater than mod Sm minus Sn whenever m and n are greater equal to n. Okay, so by using this fact, Tn is not Cauchy means it is not convergent, but Tn is sequence of partial sum of this series, hence it is divergent. So this implies that this is divergent. So let us recall what we have learned in comparison tests. First thing, if series An is dominated by series Bn, then if first result is that if series mod Bn is convergent, then series mod An is also convergent. Then series mod An is also convergent. Secondly, if the smaller series is divergent, that is mod An is equal to infinity, then we could write that series mod, let me repeat it, series mod Bn is also divergent. So in simple words, if bigger series is convergent, then smaller series is convergent, and if smaller series is divergent, then bigger series is divergent. This is what a comparison test in absolute form is. Thank you.